In this video, I want to take a look at the notion of shears. Okay. Now, perhaps the simplest way to talk about it is just to say what's going on here. That I'm thinking about the point, my two unit vectors here. So 1, 0 is going to stay put. 0, 1 is just going to be shifted over to the point K1. Okay. And so 1, 0 stays put and 0, 1 goes to K1. Okay, so there's the matrix. But the effect, notice, is that the point xy is going to go to, when you multiply that out, x plus ky is the first component of the output, and just y is the second component, right? So it looks like this right here. Now, the effect is essentially a deck of cards. So here's my deck of cards. Think of the origin as being this corner right here. Okay? And the effect of this shear is to do that each card gets shifted a little bit over. With respect to the card below it, they're all shifted the same amount incrementally each time. But that means the top card got shifted over quite a bit more than the bottom card did, right? So that's this x plus ky. That is, the x coordinate is what it used to be plus k times y. Well, the bigger y is, the bigger k times y is. So things that are higher up get shifted over more. One of the things I haven't talked about before, but was shown in some of the tables in the previous videos, is rather than just looking at what's happening to my basis elements, you can kind of look at what's happening to the unit square, right? Here, in the previous video with expansions, right, the unit square maybe got stretched into a rectangle, either that way or this way. With dilations, the unit square got made into a bigger square, or maybe a smaller square, depending on if k was bigger than 1 or less than 1. Here, the unit square is being tilted into a parallelogram. It still has, it still has the same height, right? This was height 1, this is height 1, but now it's got some non-right angles in it. Okay? Now, this distinguishes here with k being positive or k being negative, right? So you're either tilting it one way or you're tilting it the other way. Each layer is being shifted over more, right? With expansions, everything got stretched. Here, things are getting tilted. Not rotated, right? Because if this was just rotated, the length here would be the same, but this length is actually longer, right? This vector is longer than it was there. Right? So there's shears in the x direction, look like this. Of course, shears in the y direction are going to leave all the x coordinates the same, and the y coordinate is going to be y plus kx, right? So depending on how far away you are this way determines how far up you get shifted. Right? So again, k being positive would be doing it upwards, k being negative would be pulling things downward. Now, of course, on the negative side, they're only showing the positive side, but on the negative side, this would be going, things would be going up. And likewise here, on the negative side, things would be going down. Right? But the unit square is being turned into a parallelogram. One thing to notice about that unit square is the image of the unit square now being this parallelogram. The area is the same. Because if you were to cut off, say, this piece of that little triangle and tack it back on over there, you'd still have the same area. You can do shears in R3 as well. You would either shear in the x direction, or you would shear in the y direction, or you would shear in the z direction. That's kind of hard for me to do with the way my hands were. Shearing in the z direction maybe would do that, right? So in the x direction, in the y direction, and in the z direction would be shears. You can do combinations of shears in any of 2D or 3D. In fact, in 2D, you might ask, in fact, I will ask, think about coming up with the matrix that does a shear in some arbitrary direction. So if I give you a vector and say, I want to shear all of space in that direction, So if you had a square that was tilted already in that direction, then that square would be sheared to a parallelogram where the shear is parallel. So anything in the direction of this would stay in the direction of this, and anything in the perpendicular direction would be shifted over by increasing amounts. Personally, if I needed to do that kind of shear, what I would do is I would take that direction, figure out what this angle is, rotate it down to be the x-axis, shear in the x direction, and then rotate back. So I would do 3 transformations, but they're 3 transformations that are easier for me to do, and then multiply the matrices together to get the matrix for that whole shear in an odd direction. Anyway, there you go, shears.